Okay, so yesterday what we were doing is we looked at general Gaussian integrals. Well, Gaussian integrals is basically what we have in non-interacting free theories. When you write the path integral for a free theory, that is basically a multidimensional Gaussian integral. And we had this, we defined this generating function. The nice thing about this generating function was that if we can calculate it for an arbitrary j, arbitrary source term, to be honest, then we can calculate by just taking the derivatives with respect to this generating function, we can calculate arbitrary endpoint functions. And then we switch to the notation of fields. Well, that is mainly a change in the notation. Because in quantum mechanics of a single, we had, remember when we went to the field theory, we first started with quantum mechanics of a single particle, the oscillator. Then we imagined we have infinitely many of them at each space-time point, an oscillator at each space-time point. So rather than using the x of t, that is the whatever is oscillating for a single particle, we change it to phi of x, x being the 4 vector, so that is whatever is oscillating at the space-time point x. And so the action just carries along. We have been always working with the Lagrangian densities. The path integral was a sum over all the paths that the particle can take from an initial point to the final point. Now it is an integral over all possible field configurations, whatever fields we have, that starts at t is equal to ti with a given field configuration at the final time. It's a final field configuration. Those are the boundary conditions we have. And of course, we have this action is still the contribution of each field configuration. And then we said, okay, although we had some initial time and final time, what we actually want is basically matrix elements, time-ordered products of matrix elements of the vacuum of the theory. And we just made the observation that if we would like to have, these are the things that we have in our matrix element, and if we would like to have at Ti is equal to minus infinity the ground state, well, the only trick we need to do is just replace this time t by give it an imaginary time. Or, in fact, you can just multiply En and this 1 minus I epsilon, which will give you a small imaginary energy. If we do that and set the Ti to minus infinity, basically, at that time, only the ground state contributes. Even if your state has all the contributions from all possible field configurations, let's say, only the field configuration for the ground state will have significant contribution in that limit. So that is basically the trick we will be using. So we will be basically adding, you see, a small imaginary part to our energy. And another nice thing about that adding a small energy, a small negative imaginary part to the energy is, you see, now the exponent in our path integral has that part which makes sure that the integrand goes to 0 at infinite fields. So that is basically a requirement that we have. Let's see, if we go back to our Gaussian integrals, you see, here we have these Gaussian integrals. And in our case, in the path integral, these lambda i's, the parts that are multiplying the y squared, the variable squared, they are imaginary. Basically, it doesn't converge. It doesn't go to 0. So that makes the Gaussian integral kind of, defining the Gaussian integral kind of problematic. But that minus epsilon piece, this minus epsilon piece, that makes sure that the Gaussian in the exponent has a negative real coefficient. A coefficient that has a negative real part. So it makes sure that at infinities it converges, so my Gaussian integral is well defined, so it avoids many problems. But That factor is also the same thing as just adding a negative imaginary part to the energy. So by basically adding a negative imaginary part to the energy, we achieve multiple things. We are making sure that the path integral is now well defined, even in real time. And if you remember, we had also discussed that if you go to complex time, path integral becomes basically a path integral in statistical mechanics. So we can relate quantum mechanics to statistical mechanics by just going to the imaginary time. An advantage of imaginary time is that everything is well defined, everything is Gaussian, it dies off exponentially, etc. But in real time, nothing dies off. We just have oscillations. That makes integrals somewhat shaky, but adding these small imaginary parts so that oscillations die off at infinity makes sure that the path integral is also well defined. And then we were looking at the generating functionals. Now basically I asked a simple question. I have this Lagrangian, this path integral. I can always shift my integrals. And I'm just redefining my integration variable by a shift. Since my integrals are from minus infinity to plus infinity now, nothing changes. You see this integral. They should be the same. So we were asking, that was the last thing we did, what does this tell us about path integrals, about endpoint functions? And in fact, I will pick it up from here. No, sorry, this is not yet that. So what I did was, okay, we have this field clear. I mean, here I'm basically redoing whatever I had done in the quantum mechanics in terms of this field notation. I have a Lagrangian of this form, a quadratic piece plus a linear piece. And to take such a Gaussian integral, what we did was we just shift our integration variable and choose such that the linear terms disappear. And that is what I had done. And at the end of the day, I obtain my Lagrangian takes this form. My action is the integral of this new Lagrangian. Of course, I throw away total derivatives. And so this part doesn't depend on J. So this is my generating function. It separates into a part that doesn't depend on J and a part that depends on J. So this is my generating function for the non-interacting theory. That Z0 is the path integral for zero source terms, but I don't really care about that because all I care is just taking the derivatives. And then we took the derivatives. The second derivative just gave us the 2-point function, which is nothing but our Green's function, the Feynman propagator. Then I looked at the 4-point function, and remember in these taking derivatives, I take the J is equal to 0 limit eventually because that is what I'm interested in. I'm interested in a theory which doesn't have the source term. That is a term I added by hand, but then it gave me, we just made this observation that these derivatives bring down factors of derivatives of whatever is in the exponent, which is linear in J. So if a derivative acts on the exponent, there should be another derivative acting on that prefactor so that I cancel all the J terms, I get a contribution at J is equal to 0. So basically, that tells me that I have to pair these derivatives in such a way that one derivative brings down a factor from the exponent, which is linear in J. The other derivative just cancels that J, so I get a finite contribution. Otherwise, I won't get, the contribution I will get will be 0, which is nothing but our Wick theorem. Remember, in the Wick theorem, we said that if we have endpoint functions, the Wick theorem just states that we have to pair the fields and replace the fields by the propagators. Here, that becomes pairing these derivatives. I have to pair those derivatives to get a non-zero contribution. And so, well, this is what we had, in fact, obtained before. The 4-point function is just the pairwise, all possible pairwise contractions. And these G's are the Green's functions or the Feynman propagators. And then Okay, this point I will come back again. Here, that this is what I was looking for. If we just shift the variable in our integral, the value shouldn't change because my limits are from minus infinity to plus infinity. If they were not overall space, the integral might change, the limits will be different, but if I just take the infinite limits, nothing should change. And today we will see what are the consequences of this so-called, let's call symmetry. So any questions up to here? Now let's remember what the Schrödinger-Dyson equations were. From QFT1. This is last summer, the way we discussed it last semester. We had, let's say, let's start with the 2-point function. And then I just act on this with this operator. Well, if you don't pay attention to, you can just say that, let me just call this x, by the way. You can just be tempted to write this as box plus m squared phi of x times phi of x2. And equation of motion, if I have a, let's say, a Lagrangian of this form, 1/2 del mu phi squared minus m squared over 2 phi plus the interaction piece. The equation of motion I had was del mu minus del L by del phi, which becomes box plus m squared phi is equal to this one as a function of phi. So you might be tempted to say that this is equal to omega time-ordered product, whatever the interaction Lagrangian we have, its derivative at phi of x, phi of x2. Now, if we don't have interaction, that is 0. L interaction will be 0. If we have interactions, let's say if you are looking at phi to the 4 theory, this seems to give a relation between the 2-point function and the 4-point function. But this would be wrong, because you see, this box contains second-order time derivatives. And you see, time derivative of the product of two operators, time-ordered product of two operators, would be, remember the definition of the time-ordered product. This is if t is larger than t prime, it's equal to OT prime. If t prime is larger than t, it's the operator at t prime, operator at t. Yeah, well, let me just write 1 and 2. They can be different operators. And if you take the time derivative, okay, on one hand we have this contribution. But I also have the time derivative of the step functions, so I get additional contributions. The derivative of the step function is a Dirac delta. So basically, the time derivative of a time-ordered product is the time-ordered product of the time derivative plus equal time commutation relationships. Of course, if you have more than 2 times, if you have O1 at t, O2 at t prime, O3 at t double prime, you will get additional Dirac deltas when t is equal to t prime or t is equal to t double prime. And so the actual expression, this is wrong. It's missing terms. So the actual derivative will be, this will be equal to omega time ordered product of phi of x. We do get this one. Let me do step by step. We do get, for example, del mu, del 0, time ordered product of phi dot of x, phi of x, plus del 0, Dirac delta t minus t2, omega, the commutator of phi of x and phi of x2. And minus omega time ordered product of minus Laplacian plus m squared. Okay, this is what we have. Well, the time the ordered product doesn't depend on position, so I can just move the derivative with respect to position inside the time ordering without any problem. The problem is the time ordered product, the time derivative of a time ordered product is non-trivial. Well, this commutator is 0. Its equal time commutators of two fields is 0. If I take the derivative once more, I will obtain time ordered product of box plus m squared. I will get the time derivative of that term. So that is the second time derivative. I am combining it with this term over here. That gives me this one. But then I have an additional term. Plus I have t minus t2 of the commutator of phi dot, which is nothing but the conjugate momentum with phi of x. And this makes sure that the only contribution is from the equal time commutator. And when I have equal time commutator, this is equal to Dirac delta of r minus r2 with an I. So if I act with this operator on my 2-point function, I get this term, time ordered product. Over here I have a phi of x, phi of x, phi of x2, plus I, the 4-dimensional Dirac delta of x minus x2. Yeah, this is one of the Schrödinger-Dyson equations. You see, this term over here is because of my quantization condition. If I don't quantize the system, that term doesn't exist. That is a contribution from the quantum mechanics of the system. And of course, you can just do it for an arbitrary endpoint function. If you do it for an arbitrary endpoint function, what you will get will be this one. This is what you would get if you ignore quantization, if you ignore the time ordering. Plus, you will get
according to book, it's minus. Maybe because of the computation relation.
x minus xm This is what you will get. Again, this is an exact relationship, doesn't depend on perturbation theory. It relates, here we have an endpoint function. Here we have n minus 2 point functions. Here we have, what we have depends on whatever your interaction is. If you are in a phi to the 4 theory, this has 3 phi fields, so in total you will have n plus 2 functions. And in principle, what you can do is you can just, let's say, start from a 2-point function. If you start from a 2-point function, for example, this one, then here, here you don't have anything. On the other hand, here you will get a 4-point function. You can do this. You relate the 2-point function to the 4-point function, but here you can still do it further. You can relate the 4-point function to 6-point function, etc. So, and you can actually use this to obtain your perturbative expansion also. You say this term here contains one interaction term. If you apply the same procedure to this term, you will get other contributions which will contain one more interaction terms. So you will have your arbitrary point function as a series of terms that involve higher and higher orders of the interaction term. So this is what we did in QFT1. So let's see if we can have something similar in path integrals. You see, the issue here is when we have the path integral, everything is commuting. But here, these Dirac delta, so-called contact terms, they arise because of the non-commuting feature of our quantum theory. So how will we get them in path integrals? So this is my path integral. Let's say the 2-point function. Let me look at the 1-point function. This is the path integral over all fields. I'm still sticking with a single field, single scalar field. We will generalize it to more fields later on. Of e to power I, let me write the interaction as Lagrangian as d4x minus 1 over 2 phi box plus m squared phi plus some interaction Lagrangian. Phi of x. This is the operator. On the left, I have the field operator. On the right, that phi is just an ordinary function, commuting function. Now here I do the trick. I just replace phi with phi of x with phi of x plus epsilon x. And remember, in my integration measure, the value of my field at every space-time point is my integration variable. So here, basically, just pick up a space-time point x. Epsilon x will also be just a number. So I'm just shifting my integration variable by some constant. This is what this transformation is. But if I just shift my integration variable by just a constant, my integration measure doesn't change. So this remains as whatever it is. So this is equal to del phi e to power I d4x minus, this is 1 over 2 phi box plus m squared phi, no, phi of x plus epsilon of x, box plus m squared phi of x plus epsilon x, plus the interaction Lagrangian, whatever that is, phi of x plus epsilon x. These are all in the exponent. And then I have phi of x plus epsilon x. And let me just change this name. This to x1. I just don't want to use the same symbol for my integration measure in the action and this x appearing over here. I just shift my integration variable. So of course this should be valid for any epsilon of x. So you see, although on the right hand side the path integral seems to depend on epsilon of x, it should be independent of epsilon of x. So what will that tell me? I will just make an expansion of everything up to linear order in epsilon x. So in the denominator, what do I get? Minus 1, well, let me also introduce the normalization. Because since I didn't really specify this d phi, what is that measure? I mean, that measure contains all other pi factors, if you remember the derivation, pi factors, other numbers. I can always choose the measure such that z0 is 1. But let me just make it explicit. Okay, now I'm expanding in epsilon. This is just the first term. The term that doesn't depend on epsilon. Then I have minus 1 over 2 epsilon x box plus m squared phi of x. Then I have minus phi of x 1 over 2 phi of x box plus m squared epsilon of x plus the interaction term at phi of x plus epsilon of x, the derivative of the interaction term. These are all in the exponent, times phi of x1 plus epsilon of x1 plus, of course, terms of the order of epsilon squared. Now I just expanded the action in epsilon. Now I will expand the exponent also. But just note that this term here and this term, they are the same terms. If I just do integration by parts to move this box from taking derivative on epsilon, I can just, by integration by parts, I can convert it to an integral to derivatives of phi of x. So those two terms are the same. That cancels, that's 1 over 2 factor. At least now I have one less term. I have this is equal to 1 over z0, my measure, e to power I d for x minus 1 over 2 phi of x box plus m squared phi of x plus interaction Lagrangian of phi of x. These are the terms that are independent of epsilon. Then I have the exponent of terms linear in epsilon. So I'm expanding the exponent also. It will give me 1 plus I d for x times minus epsilon of x box plus m squared phi of x plus epsilon of x, the interaction Lagrangian derivative evaluated at phi of x. This is the expansion of the exponent of terms that are linear in x. These are what I have in the exponent as linear in epsilon. e to the power a small number is 1 plus that small number. Then, of course, I have this other term. Plus, of course, I have terms higher order in epsilon squared, which I didn't write. Yes.
I guess we have equal sign and again the path integral, right? Because
Yes.
we are only expanding the exponentials.
Yes. I have this equal sign, I have this normalization, then the path integral. I am expanding the integrand of the path integral in epsilon.
And then the bottom line is again equal 1 over z0 and then
Yes,
path
yes,
integral.
yes, yeah. You see, I just expanded in epsilon in 2 steps. First, I expanded the action in epsilon. In the second step, I expanded the exponent of the action in epsilon. This is one of, now I will expand that product. Well, this is nothing but my action as a functional of phi without the shift. Then I have phi of x1, this term. Then I have this term times this term, epsilon of x1. And then I have this term times all of this term. Plus I d4x minus epsilon of x box plus m squared phi of x plus epsilon of x, the derivative of the interaction Lagrangian phi of x times phi of x1. Now, what are these terms? Remember, I started by calculating in the full theory phi of x1. This is what I was trying to calculate. Now, I have this term, but that term is nothing but the same thing. But now I have corrections which are proportional to terms linear in epsilon. And what are they? Let me just write them as, I have this term. Let me write them as a d4x integral, inside a d4x integral, because I already have a d4x term over here. And so what does the first term gives me epsilon, all of these terms are contained in epsilon of x. The first term is Dirac delta, 4-dimensional Dirac delta of x minus x1. You see, here I have epsilon of x1. There is no x integral. But if I write it inside the d4x integral as integral of epsilon of x, I have to introduce this Dirac delta so that the integral will just give me epsilon of x1 without any x integral. Then what else I have? Plus or minus I. Well, you see, look at this term. That times this one. But that is nothing but box plus m squared, time ordered product, box plus m squared of phi of x, phi of x1. It is this term. And then I have this term. Again, you see, the general property of the path integral is if you have some operator multiplying the exponent in the path integral just gives you the time-ordered product of the matrix element of the time-ordered product of the corresponding operators. So that is what I'm using. And this last term is just nothing but plus I omega time-ordered product of the interaction Lagrangian, evaluate that phi of x times phi of x1. Okay. Plus, of course, terms of the order of epsilon x squared. Well, these cancel. And remember, epsilon x is arbitrary, a small function, but an arbitrary function at every point. So basically, it tells me that, this tells me that the four-dimensional Dirac delta x minus x1 minus I, this omega time-ordered product, plus I omega this should be 0 for all x. Or, no, hold on. Let me just make one correction here. Why? You see, I'm taking this x integral out. This derivative is with respect to x, but my path integral doesn't depend on x. So I can take that out also. So I should, in fact, take it out. What remains is the time-ordered product of phi of x and phi of x1. And hence, if I simplify it a bit, of course, these are all now operators. Okay. Well, it's the same equation that I obtained before. You see, the trick, well, there's no trick. I get this term. That is one of the important things. You see, that term in the original derivation is because of this commutation relationship. I don't use that information. I don't use that non-commutativity of the operator in the path integral, although everything is commutative. It is already there in a different form. It's over here. Well, what will change if you have more terms? Well, nothing really. You see, I looked at the matrix element of one field. I got the Schwinger-Dyson equation relating the two-point function to other things. If you want the Schwinger-Dyson equation for, let's say, n fields, you start by looking at the matrix element of n minus 1 fields here. You look at the matrix element of n minus 1 fields. So here you will get n minus 1 terms, n minus 1 products. And among those n minus 1 products, well, let me just sketch that also. Basically, you will get phi 1 plus epsilon 1, phi 2 plus epsilon 2, phi 2 plus epsilon, phi n minus 1, epsilon n minus 1. This notation basically, phi n is at the time, at the space-time point xn. And again, if you expand it to up to linear ordered terms, what you will get is phi 1, phi n minus 1. Remember, you were looking at the n minus 1 point function. So this will give you an n minus 1 point function. So any additional terms should give you 0. Well, what are the additional terms? We have epsilon 1 at x1, phi 2, phi n minus 1, plus epsilon 2 x2, phi 1, phi 3, phi n minus 1, etc. And you just replace, this is the first term. This one is d4 x epsilon 1 of x Dirac delta x minus x1 plus d4 x epsilon x x minus x2, this is this term, all the other fields plus etc. So you get all these Dirac deltas corresponding to the commutators with the other fields. And again, that will just give you all these terms in the sum. So you do recover the Schwinger-Dyson equations we derive using the conventional means.
Could you repeat the argument how we just put the inclined order equation out from the correlation function? Because integral was on the x variable and derivative.
Yeah, okay, so that is here. Now, I'm integrating over fields, all fields, including the value of my field at the point x. But this derivative doesn't act on the fields. It acts on the fields, but it's not acting on my integration variable. My integration variable is the values of the fields. That derivative is the derivative of the field function. So that is independent of my measure. So I can just take it out. In fact, I should take it out. What will remain inside the integral should only depend on my fields, my integration variables, not on the integration variables at different times, let's say.
The argument for that this deformation somehow should equal to 0 is a symmetry argument, right?
Which deformation?
We deformed like epsilon 1, epsilon 2, epsilon 3, and we said that this should be equal to 0. This change, right, should be equal to 0. That there should be no change. It's symmetry transformation, but it's in the correlation.
Well, it's a property of my integral. What we call an integration. Whatever the function f is. Well, I would rather talk about the symmetry of my system, meaning the symmetry of the Lagrangian. That's why I would rather avoid the symmetry term. But it's a property of the integration. If f of x is a sufficiently nice behaved function, let's say, the integral of f of x over all values of x is independent of where I choose my origin. I'm just summing over all points. Whether I call this point here my 0 point or this point as my 0 point doesn't really make any difference. I'm summing over all points. So, do you call this if you call this property of integration a symmetry? Yeah, but it's a symmetry of integration, not of the function f. Every function f should satisfy this property. That is what I'm using. And in fact, I'm stressing, let me stress it once more, every function of f should satisfy this symmetry. Every function f should satisfy this symmetry. And this is a property of integration. I will use it later on, once more. Any other questions? For example, it will be a nice exercise or a midterm question to actually show that derive these Schwinger-Dyson equation for 3-point functions. Let's give our break now. And we can start at 40. We will continue with. Well, there are a couple of things that we still didn't discuss about these path integrals. One of them will be, what about fermions? That is one thing I will discuss. Gauge symmetry. That's another thing we will discuss.
You said 40, right?
Yeah,